Hi everyone. For my review question, I went to Module 4, or Combinatorial Proofs. And so I found the question here, which is, given the function f that maps to the set 1, 2, 3, and to the set 1, 2, 3, 4, 5, 6, how many total functions are there? How many are injective? And how many functions are increasing? Meaning that is, if a is less than b, then the function of a is less than the function of b. So tackling this first question, the number of total functions. Another way we can think about this is is two-line notation where f equals our inputs, which is 1, 2, 3, and some combination of outputs from 1 through 6. I like to think of this as we have 1 through 6 total options for 1, so 6. For the second output, we also have a total of 1 through 6 options. And for 3, we also have 6 options, 1 through 6. Rewritten out, that means that a 6 times 6 times 6, which is equal to 6 cubed, which is equal to 216. Meaning we have a total of 216 total functions. For the next question, we ask the number of injective functions. So here the key word is, of course, injective. And so looking at our textbook definition, we can recall that a function is injective if every element of the codomain is the image of at most one element from the domain, and injective functions do not have repeated elements from the codomain in the range, but may have missing elements. What does this mean? Again, if we think about this in terms of two-line notation, we have our fixed inputs, 1, 2, and 3. Sums, a combination of outputs from 1 through 6. And because they're injective, we know we don't have any repeating elements, though some may be missing. And so thinking back to the same way, we have an option of 1 through 6, a combination of 1 through 6 for the first output. Because we will have selected a number for the second output, we'll only have 1 through 5. And for the third, we'll only have 1 through 4. And so this could be thought of as 6 times 5 times 4, which is equal to 120 injective functions. Now, that's one way to think about it. The other way we can think about it is a permutation, where no item is used more than once. And so we can say if n is equal to 6, then k will be equal to 3. And we can write this as a permutation of 6, 3, which written out, recall our formula of n factorial over n minus k factorial. We can say that this is 6 factorial over 6 minus 3 factorial, which becomes 6 factorial over 3 factorial, or 6 times 5 times 4 times 3 factorial over 3 factorial. And we see that the 3 factorials cancel out, and we're left with 120, which equals 120. And we can see that this 654 matches this 654 over here. Awesome. And then our last question is the number of increasing functions. Keyword here is increasing. Because, and let's think about this again in terms of two-line notation of f is 1, 2, 3. And so because it's already written as increasing functions, we just have to worry that our output is also increasing, and that no item is used more than once. And so from there, we can think of this as a permutation. So we can think of n equals 6 and k equals 3. So I'll write this as p, or permutation of 6, comma 3. And recall from our equation, that means that we'll have 6 factorial over 6 minus, 6 minus 3 factorial times 3 factorial. Written out, we see that that's 6 times 5 times 4 times 3 factorial over 3 times 2 times 1 times 3 factorial. And this 3 times 2 times 1 comes directly from the 6 minus 3 factorial. Simplifying some things out, we have 3 factorial over 3 factorial, which cancels out. Then we know we also have 3 times 2, which equals 6. And so we can cancel out that 6 and 6, which means that we're left with 5 times 4, which equals 5 times 4 over 1, which equals 20. Awesome. And so we have 20 increasing functions.